Today I'll talk about the statistics of kmers from a sequence undergoing a simple mutation process without spurious matches. This is joint work with Antonio Blanca, Robert Harris, David Kozlicki, and myself, and it's based on a preprint that's available on bioRxiv. In this talk I'll introduce first the model, and then give a few motivating applications of where it's used. We'll then look at distribution of the number of mutated kmers in this model and conclude by showing how that distribution can be used to derive a confidence interval. We'll then look at other random variables in this model and show some experimental results. So let's look at the model that we're going to be working with. We start with the genome A, and then we mutate every nucleotide with some probability R1. And this gives us a new genome B. So here I'm showing the mutations that actually happened as red crosses here. The one key assumption that we make in our model is that all the kmers are unique. In other words, A does not have any duplicate kmers, and any of the new kmers that are created as a result of the mutation are also new with respect to A. Now, we don't actually observe the nucleotide sequences in this model. What we observe are the kmers that belong to those sequences. And for algorithms that work with de Bruijn graphs or just in general that are kmer based, this is often the case. Well, one variable we might observe actually is the number of mutated kmers. In this case, there would be 8 mutated kmers. And I visualize this using these little red and blue circles. Each one of them represents a kmer starting at that position. So this, for example, is the last kmer here with k equals 3. Now, a single mutation like this one also affects 3 kmers. So each of these kmers are also mutated. Whereas here, these two nucleotide mutations affect 5 and mutate 5 kmers. Oops. So another variable we might look at is the Jacquard similarity. The Jacquard similarity between two sets of kmers is simply the fraction of kmers that are shared. And in this model, this simplifies because the only way we can generate a new kmer is through a mutation. Otherwise, the kmers are shared. So the Jacquard similarity becomes L, which is the number of kmers in every sequence, minus the number of mutated kmers divided by L plus and mut. Another variable we might observe is the min-hash Jacquard. So the min-hash Jacquard works as follows. First, you create a min-hash sketch of A, and you create a min-hash sketch of B. And then you measure the Jacquard between the sketches. And we call that J-hat. Now, a well-known classical result of Broder states that this J-hat is an unbiased estimator of the true Jacquard between the original sets of kmers. Let me give a couple of applications which motivate the use of this model and have used it themselves. The first is match distance. In this scenario, we take two evolutionarily related sequences and we observe the min-hash Jacquard estimator from them, the J-hat from the previous slide. We make the assumption that the genomes evolved under the simple model, and we try to estimate the mutation rate R1 from this J-hat. And this is what the MASH paper does, and it's great to have this kind of point estimate, but wouldn't it be better to have a confidence interval for R1? What I mean in this case is that given that we have these two sequences that evolved under the simple model, we observe and mute, what is the interval that will contain the mutation rate, the true mutation rate, with 95% probability? So for example, this could be between 0.05 and 0.07. Another example is the alignment of reads to a reference, where the reference is represented by a de Bruijn graph. In this case, we're working again with kmers rather than individual nucleotides. In this scenario, the read is generated from some genome location, but there is a sequencing error rate R1, and our simple mutation process actually captures this. What an aligner then wants to do is take a putative location for the in the reference and ask, could this have generated the read? And what it observes, since it's using a de Bruijn graph, is n-mut, the number of mutated kmers, and it wants to then accept or reject this putative alignment with 95% chance of being correct. In statistical terminology, what we want is a hypothesis test with significance level of 95% for n-mut. In other words, given R1, what is the range into which n-mut would fall with 95% probability? So in this case, we observed n-mut being 8, but given that, say, R1 is 0.01, we might see that the range for n-mut would be between 3 and 7 with 95% probability, so we would reject this alignment. A key difference between these two applications is in the first one, we don't know R1. We're trying to estimate it. In the second one, we actually know R1, right? And we observe n-mut, and it's either outside or within our hypothesis test range. Now let's look at the distribution of n-mut, because this is a starting point for a lot of analyses. We can express n-mut as the sum of Bernoulli random variables. In this case, we let xi be the indicator random variable, in other words, it's 1 or 0, that indicates that kmer starting at position I is mutated. So in this picture, each of the circles corresponds to an xi, and a blue circle is 0 and a red circle is 1. And then n-mut is just the sum of all the xi's. And if we want the expectation of n-mut, that's pretty straightforward to calculate using linearity of expectation, where it becomes L times what we denote as RK, which is the probability that a single kmer is mutated. Now, that's where all the papers I'm aware of stop, but we wanted to understand this distribution a bit further. Now, you might think that n-mut is a binomial, and a binomial is a sum of independent Bernoulli trials. Now, in this case, nearby xi's are not independent. Like these two guys are dependent. If I know here that I am mutated, it increases the chance that my neighbor is mutated. However, xi's that are far away are independent. And we can capture this notion in this dependency lemma, where we formally write down what the dependence is and what the far away means. From this dependency lemma, we can use some straightforward but tedious algebra calculations to derive the variance of the n-mut random variable. So it already goes farther than just knowing the expectation. Now, if this was a Bernoulli random variable, we would take the expectation variance and use a normal approximation to compute the confidence interval. But in this case, we don't have that independence between trials. However, we do have something that's called a bounded dependency neighborhood, which means that the random variables are dependent, but each one is dependent on some bounded number of other variables. And what's known in the literature is that the sum of such variables is asymptotically normal. And knowing that, we can then derive a hypothesis test and confidence intervals using the same strategy as we would with a binomial. Okay, so that gives us this theorem, which I call the main technique theorem because it's what we apply a lot in the paper. So let x be a sum of Bernoulli random variables with this bounded dependency. Then the variable x lies in the interval centered around its expectation plus minus this term with limiting probability alpha. So let me break that down. First, by limiting probability, I mean as L goes to infinity. And the star here indicates that there's some other smaller assumptions that I make on the relation between L and K and R1. Now, this term is the square root of variance and the z-score, which is something that can be computed in any programming language or a table lookup. So this gives us the hypothesis test for where x is going to lie with probability alpha. We can immediately apply our main technique to the nmut variable to get a hypothesis test based on the variance that we just calculated. To compute the confidence interval, we just have to invert this equation to solve it for R1. Algebraically, this is challenging to do, but we can do it numerically, and we have a theorem in our paper that states that the numerical algorithm is actually correct. We can then also apply this main technique theorem to not just nmut, but to any random variable that is a monotone function of nmut. So Jacquard, for example, which we've seen earlier, is in this model a monotone function, and we get this hypothesis test for for the Jacquard. We can apply our main technique to other random variables in this model. For example, islands and oceans, terminology that we borrow from Landor-Waterman statistics. An island is a maximal interval of mutated kmers. So like in our example, we have here 2 islands in red, and oceans are the non-islands, the blue. And so any sequence can be partitioned into alternating islands and ocean, and our main technique allows us to also give hypothesis tests for the number of islands and the number of oceans. Another variable is the min-hash-Jacquard estimator. And here it's a little bit more complicated because there are 2 layers of randomness. First is the mutation process, for which we can apply our main technique, but then there's the randomness due to the sketching process. And here the main technique doesn't work because sketching uses global information and therefore creates a larger dependency neighborhoods. We use a different approach, which we won't be able to get into here, but we obtain a similar theorem hypothesis test for the min-hash-Jacquard estimator. This is the summary of our theoretical results, and I've already discussed all of these except CBER, which is the coverage by exact regions, a variable used by Miklot et al. In their Java error correction tool. Let's look at our experimental results. So first we tested how well our theoretical confidence intervals for nmut are in how well they perform in practice. We did a simulation where we basically simulated the model that we have. We started with a sequence with no duplicate kmers, and we varied k and r, and for each value of k and r we did 10,000 replicates of the following experiment. We ran the simulation model with the given R1. We observed the nmut. We used our theorem to predict R1. And then we measured whether the true R1 falls into our predicted 95% confidence interval. And you can see that for a sequence length of 10,000, it performs really well. For a sequence length of 1,000, it's still performing really well. And when L is only 100, now you see some of these are not performing well, and this is where the kind of as L goes to infinity assumption is starting to break down. We also wanted to test this in a situation where our assumptions do not hold. So we use the coli sequence, which does have duplicate kmers, and we see that the results hold in there as well. We then looked at our estimator for the min-hash-Jacquard, or for the MASH distance, and we essentially recreated a table from the original MASH paper, but instead of putting the point estimate in each cell, we did the experiment as in the previous slide, where we measured in practice how accurately our predicted confidence interval captures the true R value. And this was for varying sketch sizes and varying R1s. And again, we see we're doing pretty well, except for some small sketch sizes and more extreme values of R1. We also did this test with E. coli instead of a a genome without repeats and got similar results. We then tested the application with alignment to a De Bruijn graph. So the Minimap2 tool sometimes filters out alignments if the R1 estimate is far from the error rate, and it has its own way of estimating R1. Instead, we can use our model to come up with our own R1 estimate, and as this plot shows, our estimate, which is in blue, has a smaller error than the Minimap2 estimate, which is in red, across different values of R1. In Java, which is a tool from McLeod et al., which I mentioned earlier, they also have a way of filtering out alignments, but they don't use R1 estimate, but they measure instead the coverage by exact region, this CBER, and see if it significantly deviates from expectation. However, they don't really say what significantly means, how to interpret it precisely. And using our paper, we can define a theoretical hypothesis test for CBER. And like in this plot, you see the two lines above and below are giving the 95% confidence interval, and we can filter out alignments that fall outside of that. So to conclude, we studied a simple mutation model. It's been widely used but never studied in depth as far as we know. And then we show how in this model, there is a technique for deriving hypothesis tests and confidence interval. And this technique exploits the fact that the kmer dependencies are bounded. We apply this technique to a few natural random variables shown in the table below, but we hope this technique is more broadly useful for others studying kmer-based methods. And with that, I'll conclude the talk and take any questions.